I done messed up.
Huh?
I think I done messed up.
How'd you mess up?
It's got me on drawing.
Well, I thought it'd be easier to use. If
Well, I can't start my PowerPoint. All it's going to do is let me draw.
that's
There you go. That's a good idea. Let's see if it pops back up there. No. Oh, it got rid of it also. This is what we're going to do, describe the function of subroutines. What do we use subroutines for? Why do we use subroutines? What's the function?
organizing your program.
Yeah, it's technically referred to as structured programming.
Yeah.
And the more structured your program becomes, the easier it is to troubleshoot, and the easier it is to modify, right? Y'all understand that? We originally started working in a programming language called BASIC, and you had to put line numbers beside each one of them, and you had to start. Originally, you had to put the line number in there, and you'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then you wanted to come in and modify it, you couldn't. If you wanted to insert an instruction, there was no way to insert an instruction. So they decided to take that away from us and automatically start with 10 and go 10, 20, 30, 40, and then you had what? You had 9 additional lines you could put in there. Because they were figuring out, okay, we got to make, and then the programs kept getting longer and longer and longer. One of the, when IBM first started contracting out for people to write applications and operating systems for them, they paid the people in what they call KLOCs, which was thousands of lines of code. So the problem they had is that, and Bill Gates changed that because he said, oh, okay, so you're telling me if one company does it in 1,000 lines of code and I can do the same thing in 100 lines of code, you're going to pay me less. So people would deliberately make these big fluffy programs that would take forever to run because they got paid by the number of lines of code. But what we found out real fast is that we needed a way to organize our programs because they got so long, right? You understand? So they came up with a method called subroutines, where we can take large programs and we can split them into individual little programs. And also, what Windows came up with a method is where we could share subroutines between applications. So if you ever look at the directory, and I don't see it here, but let's go to C, and let's say program files. I can't see it. But if you ever look at these guys right here, DLL, Data Link Library, those are just subroutines. But they're available to any program. They could go out there and say, well, I need to use this subroutine. So like Windows, they've got, Microsoft Office, how many applications do they have? Well, they got quite a few applications. How many of them have to print data? Every one of them. Well, instead of me writing the whole subroutine inside that program, then I can just call the subroutine that's already out there and do what? Have that. So it's a lot of methods that we can utilize these subroutines. Right now, I can't figure out how to. I know you can do that with the new versions, and they call them libraries. So what we can do is we can set up a section of libraries and these common subroutines that we use. Instead of me putting them in my program or rewriting them, I can just do what? I can just access them through libraries. When the RSLogic 500 doesn't give us that aspect, but as we move on, then things start changing, right? You understand that? So it makes the program what? More manageable, basically. Makes it what? Easier to edit. It makes it easier to troubleshoot. It makes it because we can go to a section where these things are identified. And I think I showed y'all the actual Allen Bradley and it's RS500, the Logic 500 that's actually running the manufacturing line over there, the Festo line. So these are the actual PLC programs that's running the manufacturing line. Oops. Oh, here we go. PLC programs. And then this. So these are all the different modules over there. And this is normally what we do is we set up what they call a main program, a main loop. Now, in Allen Bradley, your main loop is going to have to be ladder 2, which is what we automatically get. When we start a new project, you automatically get ladder 2. So right now, the only one y'all been working in is ladder 2, right? And I showed y'all how you can give it a name, right? So once you got a tab, when you create a new program file, you're going to be given the option of giving it a name. Ladder 2 comes up unnamed. So how do you change the name if you want to? Yeah, just go down to the tab and then right click on it, and then it'll pop up and say, do you want to do what? Change the name, right? Everybody okay? And then you can give the tab a name. Now over in your project tree, it keeps up with the ladder it is, because what happens is that when we come over here and send it off to a subroutine, what we do is we send it off to a file number. And that file number corresponds to this ladder number right here. Does that make sense? Everybody okay? And by the way, and when you bring this up, I don't want to rename that because that might, well, when we bring this up, the only part, and by the way, and I think Milton brought this up. He got a real good idea. Is that you, Milton? We're going to try to put another tab here and put another program. Well, what you have to understand, was it Bernard? Who was that? Yeah, so he said, okay, I'm writing this program, and I want to write another program. Why can't I just make another tab and make another program? Well, that's not another program. Anything in any tabs down there are part of this program. So if I made a tab back there and I didn't put a jump subroutine out there, then that sucker would never run. So if you're going to make a new project, then you got to create a new project. So any tab you make down here is part of what? The same program, right? It's part of the same program. Are you okay? By default, it only opens up the last tab you had open, so it'll come up on this one. And if I want to look at these other, the subroutines themselves, I just come down through here, and now I've got them all opened up, right? And I like to open them up in the same order that they are. So your original program is going to be ladder 2. Your next one would probably be what? 3, 4, 5, and 6, right? You understand that? Okay. But you don't have to go in that order because it gives you the option of assigning which tab you want it to be at. But if you say create a new program file, then it's going to give you the next available tab. Unless you're dealing with the 1000s. The 1000s comes up, and remember the 1000s is a really cheap PLC. So if you deal with the 1000s, it's going to come up here and give you all the ladder that's already available. And you cannot create a new one. So I can't remember.
Even that's fixed?
That's fixed inside that fixed PLC. So if you're using the 1000s, I don't remember. There's a few. It'd be plenty for this class. But see, I think I told y'all that PLC costs about $150. So there's a lot of things that they do with that PLC that they don't give you the option. So it don't have a lot of memory in it. And, are we okay? So on this one, this is the 1100 that we're dealing with. Well, actually, these programs are written for the 1500. So I can download this one into this PLC because this is the 1100 PLC. Right? You understand? Everybody okay? You can rename these tabs if you want to, so you can name them when you create them, or you can rename them anytime just by doing right clicking on them and you can give them another name. Everybody okay? Now, how do we get to the subroutine? Well, what we do in our instruction is we come up and we put a what? Subroutine. Now, in your list of instructions, in what category, what group is this going to be in? This is going to be in the program control group. Did I go past it? Yeah, program control group. So here's your JSR. Here's your jump. Jump, we talked about that last class. But we're going to deal with two instructions, or three. And they don't use it. We're going to deal with the JSR instruction. And we're going to deal with the return instruction. So what you have to do if you go to a subroutine, you're in a different program file, you have to tell the PLC to do what? Come back. Make sense? Then you have to go, then we're going to deal with an SDR. This identifies the subroutine. So this is an optional instruction. The book says it must be in there, but it's optional. Normally we use this because it identifies a tab as a what? A subroutine. Everybody understand that? It's called SPR. I have to look it up, but it's the subroutine. It's the first subroutine. Yeah, and what it does is it's an input instruction, and you know every input instruction has to have a what? An output. So normally what we do on the output is because it's true all the time, right? You understand? So what we got there is we just use one of our bit files that we're not going to use. We use one of our B3s or B10s if it's available to you. Okay. So when we look, and it's optional. The book don't tell you that, but it's optional. So if I look at this subroutine, notice what they didn't have. And it's going to be the first instruction, so it'll be in rung 0. It'll be in rung 0. So this is actually a subroutine that's being called by what? What we call the main program or the main program loop. So when we get back to ladder 2, this goes to subroutine 4. So that would be 2, 3, 4, or you can look over here, right? So this goes to what this PLC happens if we initiate a emergency stop. And you can see what this guy does. It just outputs. I know I have to look. It sets this up to 0, so that's a constant. Sets this to B3. Why they did that? Length of 3. Oh, this is a field. So what they did is they fill 3 output ports, or they fill 3 words with nothing but zeros. We haven't looked at the field yet. Then they come up and they fill what? So they're clearing out a bunch of memory. And then they're going to take 0 and put it into this output word right here. One word. So it looks like they're going to just clear all the outputs off. They're going to turn all the outputs off, or make them false. Of course, the last instruction on a subroutine has got to be the what? Return. Does that make sense? On any of them. On a subroutine. Yeah. And we have several different types of subroutines. We have interrupts too that we'll look at too.
Other than those return back to you.
Because it goes back to where it calls. So what we have inside the processor, and we don't really have control of that, is there's a special memory that the processor can use without me telling it to use it. Okay? And it's called the stack. It's called the stack. And we can set up a stack, and we'll look at that later. We can set up 2 types of stacks. We can set up what we call a last in, first out, or a first in, last out. But what happens anytime it sees a JSR or jump subroutine, it automatically creates what we call a stack. And you can think of a stack kind of like these places when you go into these buffets where they got the plates over there and inside this big old thing, right? And when they come up here, they put them on the top, right? You understand? And then what do? You pick one up, and then it automatically shifts up, right? And that's what a stack is. So what it does is sometimes the processor has to automatically know where it can store and retrieve data. So primarily a stack, most stacks are what we call last in, first out. So whatever you put on there last would be what? The first thing it pulls out. Now what it's got to keep up with, and let me bring up the PowerPoints. Subroutines, we have what we call unconditional subroutines. So we could look down through the ladder for the, so this right here would be considered to be a conditional subroutine. Why? Run zero. This would be a conditional jumper. This would be what we call a conditional subroutine, because conditions have to be met before this subroutine takes place. Now look at this sucker right here. There's nothing in the control. This is an unconditional jump subroutine. So the first one in run zero will only occur if it meets these positions right here. If there's not an interrupt, right? You understand that? They're using so Pesco don't quite do this right. Why is that? Because they're using the examine if open for the interrupt. This is the e-stop button they use. So they have the e-stop. Our Festo lines with the Allen Bradley PLCs, they don't have an e-stop on there. They don't have an e-stop. So they make this run true all the time. But when we went to these guys now, I've never seen an e-stop like this. Here's the e-stop on this one. And what you do is you pull this little thing out. And so what we would find out on this one, it would be okay if they had like a cord or something on it, but you got to think about it, you know. And I was telling Thomas, I was thinking about actually putting a real e-stop on the front of it. So this at the top, this would be considered a conditional JSR, right? This would be considered an unconditional JSR. So anytime you put an input instruction, you have to have an output instruction. But an output instruction doesn't necessarily have to have an input instruction, right? You understand that? Everybody understand that? But as soon as I put some type of control device in front of it, it becomes what we call conditional. And that's one of the problems I had with the jump instruction. So this guy would be unconditional. It's going to take it out to subroutine 6, which would be this guy right here, which is going to cause something to blink. And then I can't remember the rest of them. I don't know what's going on with my computer, guys. It's kind of slow. Is everybody okay so far? All this makes sense. They talked a little bit about the stack, structured programming. We talked about the programming. Programs that are written in subroutine can be tested individually to ensure accuracy. Easier to troubleshoot and maintain. It can be called from the main program, but this is it can be called from anywhere. So we can have a subroutine call a subroutine. And that's what's so important about the stack. It's the last in, first out. Right? Does that make sense? We call it nested programming. So this would be a typical subroutine way. So we're running down our main program, calls a subroutine. What does it do? Well, it saves the return information on the what? No, it saves it on the, how does it know how to get back?
The return.
So how does it know how to get back? Well, when you call the subroutine, what it does is it automatically puts the condition of the processor. It puts the registers inside the processor, the program counter that keeps up with the count, and it saves that on the stack. And then when it hits that return, it automatically does what? Pulls it off the stack. And that's automatic, guys. We don't have to do anything. So what happens as soon as it sees a call, what it does is it saves the condition of the processor on the stack. Then it loads the counter with wherever the new subroutine's at. Then it jumps down here. Then it runs the subroutine. And then when it sees that return, what does it tell it to do? It tells it to pull all the information back off the stack. And where will it take it back to? Well, it's going to take it back to the next instruction or the next run after the JSR. And then it's going to start running the main loop again. When it sees another JSR, what's it going to do? It's going to save where it's at. It's going to save the rung it's at, right? It's going to save where it's at. And then it's going to do what? It's going to go run the subroutine. And then when it hits the return, it's going to pull all that stuff back off the stack and go to the next run. Everybody okay? That makes sense? It's pretty neat. So the stack is invisible to us right now because it's automatically created anytime it sees a JSR. But we do have the ability to use the stack ourselves. Not this stack, but another stack. We have a user stack that we can set up. Subroutine. Output instruction. Unconditional no control devices between L1 and the JSR construction. Then that should be over. Conditional, what happens? We have input instructions between L1 and J. Input instruction or instructions between L1 and the JSR output instruction. SBR, this is an optional instruction, even though the book doesn't say. We should use it because it clarifies, normally it clarifies what the subroutine is, right? It identifies it as a subroutine without having me to go down and see the return. That makes sense?
It does. Could I get that last part?
It identifies it. So I've got all these, these big old programs right over here. I got all these little tabs. We got at least two types of subroutines we can run. We can run what we call interrupt we can have what we call interrupt routines. They end with a return. And then we can have these subroutines. They end with a turn. Well, if I don't understand that, if I can't put something up at the very top that says, okay, this is an interrupt subroutine or this is a standard subroutine, then I can get really confused real fast. So what they do is they recommend that you use these. And that way, even though they're optional, they recommend you use it so that when I go across those tabs and I see SBR, I know it's a standard subroutine. If I see INT, I know it's an interrupt subroutine, right? Y'all understand? And I don't have to figure that out because if I see an RET at the bottom, that doesn't identify what type of subroutine it is. So we have two types we got. We got what we call an interrupt subroutine, and then we got this guy right here. An interrupt subroutine, an interrupt is generated by hardware. Right? Y'all understand? An interrupt is generated by, we got things that I don't need to be able to put into a program. My hardware needs service. So right now, I've got all these programs up here, all these programs running, and I got this keyboard down here. Is my computer running the keyboard program right now? No, because I'm not doing anything. Why would it waste time to check to see if I press a key when I can come up with a method where I can tell my program when I press a key? So what happens when I come over and hit this key, it generates an interrupt. And now the processor says, okay, something's going on, right? You understand? So what we do with hardware interrupts, it gives us the ability not to check this stuff all the time, like maybe not even check an input, maybe not even run this over here until something happens. But the hardware has to be able to let us know when that happens, right? You understand? So an interrupt would be like me up here. So the way they used to run, and as long as when they first came out, was the processor had to scan everything. So they'd have to stop every once in a while, and it'd be like me going to everybody in the class and say, Christine, do you have a question? Bernard, do you have a question? Milton, do you have a question? Brandon, do you have a question? And I'd go through all my inputs. I'd say, do you have a question? Which is what the scan's doing. The scan's going to every input and saying, are you true? Are you false? Are you true? Are you false? And that's the way the PLC's running, right? You understand? What would be the better way to do it? for me to get up here and teach, and if you have a question, you interrupt me, right? You understand? Now, in a formal classroom, you'd go what? You'd raise your hand. Okay, so that's hardware. That's not me. I'm not stopping all the time going to everybody in the class like the PLC scan and the scale. So that's what's happening. It says the scan's the input, and that's what the programs are doing. It's going to every input and saying, are you true or are you false? Are you true or are you false? Are you true or are you false? Right? You understand? And it works okay for standard inputs because I'm going to look at it all the time, but it don't work for when a device says, hey, I gotta be serviced right now. So we have these interrupts that the hardware can do what? They can raise their hand. Hey. Now we have the ability to turn them off, right? You understand? We have what we call enable and disable the interrupts. So if I'm doing something important over here, it's just like when you raise your hand, I don't stop. I try to do what? Complete my thought, right? Like Tom was doing this the other day. He was interrupting me, right? And I said, okay, I know it, Thomas, but I said, what? I need to finish my thought, right? Yeah. So what I did is I did what? I disabled that interrupt, but when I got to a point where I could do what? Where I could honor it, I enabled it and it was still out there. So it's pretty neat. So hardware interrupts, but it works just like a subroutine. It's just that instead of me calling an interrupt, it's generated by what? Hardware. But it ends with an RT. Because it ends with a RET too. So if I don't put what type of interrupt it is up there, if I don't put if it's a subroutine or an interrupt. So we have these two optional headers we can put up there. We can identify the subroutine. We can identify the routine as a interrupt service routine, or we can identify it as a call subroutine. So this is optional, but we need to put it up there. So I'm gonna want y'all to put that up there. And since it's an input instruction, it's going to require what? Output. So usually what we do is we just use one of our B3 registers, B3 or B10. I'm not sure if the 1000 supports the B10. I know the SLC 504s do. The return, this has got to be there. This is the last instruction before the end. May be conditional. If condition is not met, subroutine will loop. So if you don't want to return, you can just make it do what? Yeah, it'll just loop right in that subroutine. So this is one thing that we normally do when we're trying to set up a module, is we just write it without the return, and now we can just run that sucker as many times as we want to, right? You understand? And then do what? And then when we're ready, we can just put the RTE in there. But we can make this conditional. Sends the program back to the instruction in the rung immediately after the JSR. Creates a number of program files in the project tree. Note that ladder 2 is created automatically when the project is initially created. Note that on some fixed PLCs, the number of subroutines available are fixed. So that means when you look at the 1000, it's going to have a bunch of program files over there already. And that's it. That's all you got. You can't do any subroutines past that on the 1000. The 1100s and the 504s, you can make as many as you got in. Okay? Right click on the program file, listing in the project tree, select what? New. Next, available program file will be listed starting at 3. Give it a name. The name's optional, but if you don't give it a name, then you don't know what, if you leave it at file 3, so it'll come up and say ladder 3, ladder 4, and now you have no idea what these subroutines do. So what you need to do is you need to give that thing a name, right? You understand that? So that way you can look at the tabs and you tell what they do. That makes sense? By the way, they'll open up in the order you double click on. So if you take ladder 3 and then you double click on ladder 4, it'll put ladder 4 right beside ladder 2. And now they'll be out of order, but if they got names, you still know what. Yeah, which one it is. Holds the program counter. So we don't know about the program counter, but inside the microprocessor, it uses a register inside the microprocessor called the program counter. And that's exactly what it does. It just counts through the program. It's always one step ahead. So it'll output the address and it goes ahead and increments to the next rung until, cause it's ready to go to it, right? Understand? Holds the address of the next instruction that is going to be executed after executing instructions in the subroutine. The return instruction at the end of the subroutine causes the information to be pulled, some people call it pop, from the stack, which makes the subroutine program return to the call-in program file next to the rung after the JSR. Now I didn't put the main program, I said the program file, right? So we can have a subroutine call a subroutine. Continues the next instruction in the program they called it. Prior to the jump, the subroutine module, the PLC processor, creates something called a stack. And what is a stack? A stack is just a group of memory locations that the processor can automatically access without you specifying. That makes sense? And every processor that I've dealt with for a long time has a stack. Some of them have more than one. We have a register called a stack point. Holds the program counter, flag registers, and general purpose and pointer registers. So what it's doing is saving the condition of what that processor was doing before you call the subroutine. Once it's saved, then what can it do? It can pull that information back off the stack, and then it'll return to exactly what it was doing when it left. The JSR causes the processor to first create a stack, save the program counter, flag register, general purpose register, pointer register, starts executing the instructions in the subroutine. And then what does it do when it sees the return? It just pulls all that information off the stack, right? This makes sense? Everybody's okay so far? Pulls the return instruction, pulls the contents of the memory out of the stack, places the contents back in the processor register, program execution in the program. I need to take out the main program, then resume. Now next is the next slide. We'll look at this. So this is the program that they got in the book. So would these be conditional jumps or would they be unconditional?
Conditional.
These will be conditional. Right. So that means if I would come up here and close this switch. So if I didn't close any of the switch, what would the PLC do? But it's going to do something. It's going to be just doing what? No, it's just going to be looping, right? It's going to be looping. It's not waiting, it's looping. Right?
I mean
The actual PLC scan. It's still going to examine inputs, run the logic, update outputs, scan the inputs. It's just that nothing's happened. So this guy's just looping, right? Waiting on me to do what?
close it.
Close a switch. This is switch 1. This is switch 0. This is switch 1. And it shows you how to do that. So what y'all need to do, right click, click on program files in the project list. Right click on it, right? You understand? Then do what? Click on new. And then this one will pop up. Next available program file will be this number right here. Then you're gonna give it a what? Name. Then you have the option of putting the description there, which would be pretty good. So you could actually put a more detailed description. I usually don't use that. What I do is I usually put a run comment. Y'all know how to put a run comment, right? Well, when we come over here, if it works for me. So when I come up here and right click on this, it gives me the ability to give the ladder a title. So you can put a title across the top. Then it gives you the ability to put a comment about that run, right? So you can see this is what they did here, and it used to be in German. I'm working with it too. Is they came up here and they tell me, call in emergency stop in condition of emergency stop signals. And so this is a comment that they gave on this run which makes it easier for other people like me to figure out exactly what that run's in there for. So to create a comment, all you have to do is go onto the run, right click on it, right, and set edit comment. And it'll pop another box up there. And you can do what? You can type in whatever comment you want. And I don't know any limit. RS Logic Pro limits you to one line. But RS Logic, as far as I can tell, don't. I hadn't hit the limit yet. Of course, I had to. This is the label for this. So this, you can't tell it, but they're two different colors yet, yellow. And of course, this is the symbol bank, right? So you can give it's not a comment, they call it a label. You can give every one of them a label, and you can give every one of them a symbol, right? So this is pretty neat because now you can identify exactly what the symbol means. And then if you do this, then you come back a year later, even I've done that before. I wrote a dang program, and came back, and I said, what in the world did I do that for? Why am I doing that? Or well, how's this thing work? Because I didn't do what? I didn't put all these comments and everything in there that would make it easier for even you to come back in a year or next week and say, well, why did I do that? Or what's this, that, and all that kind of stuff. So it's really good to make as much document as you want. And if you do print this off, and y'all don't have the ability to print this. If I can remember how to do it. So what you do is you go to print setup. No, that's not it. Print. I don't want to print report because what I'm going to do is going to print all my labels. It's like 30, 40 pages long.
Did you label that in there?
Yeah, when we come up here and do this, we got two options here. Okay. So when you create it, you have two options. So let me close this out before I screw it up. Huh? Yeah. Okay, so we got to what? New. And the first thing we do is what? Select the processor. Yeah, select the processor. And then, by the way, if we have additional modules, so the 1100 is what I call a hybrid PLC. Alan Bradley still calls it a modular PLC. But we have the ability to slap modules onto the side, right? Well, once you slap another module on the side, then what you would have to do is you'd have to go, now you're going to have to go to the IO configuration, and then you have to select the module. So it's kind of like the other one. The only difference is you don't have to identify the size of the rack, right? Everybody understand that? Which is pretty neat. By the way, if you're on the 504s, you might want to try this. Supposedly, once you've established communication with the PLC, you can, from what I understand, you can come up here and it'll actually configure it for you. So y'all might try that once instead of trying to go to your inputs and your outputs. Once it communicates with the PLC, then the PLC can go out and figure out what type of modules you got. So y'all try that one time and let me know if that works. So what we have to do now on the 504s is you have to go up there and say, I've got a 7-slot rack, and then you have to identify those things. But according to what I've read, you get on that IO configuration. But you have to be connected to the PLC, but every one of y'all has done that so far. But we could go in and we could actually try that. Of course, we don't have any extra modules on this, even though. So when we come up here and we insert an instruction, and it don't make any difference what we put in here. Let me put a new run in there first. As soon as we get this, we got two options. We got this guy right here, which it automatically goes into. Then I can come up here and I can put, and then I can come down here and then I can give it a symbol name, which is usually going to be some type of command, right? And then notice what happens is the first thing I gave it comes up as a label. It's just, it helps me do what? Clarify what that thing actually does in life. And then the symbol allows me to address it with very few letters. So your symbol names, you don't want them to be real long. You want them to be real short, right? You understand that? To make them easy to type in. You put a 15 character symbol name, you might as well drag the symbol down, right? You understand that? You can edit these once you do that. So if I come up here on the yellow one and then I double click on that, then only thing I'm doing is editing the what? The comment, yeah. And if you come up here and hit on this one, then it's going to let you, all you're going to do is edit the symbol. Are you okay? And then I can come up here and I can right click on this, and then I can come up here and give my whole diagram a title. By the way, this will come up too, and I can call it, Now what this will do is it'll pop up at the top, and what we just did is what? Yeah, we've given this program file a title, which would also make it easy. And then I could also come in here and start putting comments in there. By the way, when you do the comments, you can also do a comment for the run. You can also give it a page title. And of course, but you can give a rung, each rung a what? A comment. And then later on, that would help you do what? Yeah, come back and do that. The return SBR, the SBR instruction at the beginning of the program indicates that this is a subroutine. It doesn't, but it's what? Optional. We recommend that you use it. Return output instruction at the rung before the end, rung that causes the return of the PLC to the calling program. Are we okay? Subroutines in most industrial application lengthy programs, and we've already talked about this. Ladder diagrams are usually divided into what? Several subroutines, and that's what you find. Certain sections do certain tasks, and that's what you try to do. You try to divide. You don't just randomly go out and pick out. So, well, I'm gonna put these first 10 in this subroutine. I'm gonna put this first 10 in this subroutine. What you try to do is you try to figure out what different tasks your ladder is going to do, and then you put each task in the subroutine. And then you give that thing a name according to the task that it does. Right? Does that make sense? And that makes it extremely easy. Like I think I told y'all, the robot that runs the Amatro line is an extremely lengthy program. But what do? They subroutine. So now, and we had a problem when we moved the line from one side of the room to the other side of the room, that the floor is not level, and the module for the robot was up out of the way. So I had to reteach all the points. Well, if I had it in a program that's 100 lines long, then I'd had to single step through that program and find where it did that, right? Understand? But now I just did what? I just went to the subroutine, and I could keep running that subroutine and verify the point and everything until it was right. So subroutines are what called structured programming. So this would be conditional subroutines, right? Here they're using what? They're using compare instructions. This would be definitely conditional. So they got a counter, and if it's equal to 10, they will run this subroutine. If it's A is less than B, it'll run this subroutine. If A is greater than B, it'll run this subroutine. This will reset the counter. Are we okay? Then I think what they do in the book, the textbook, is they show you these little short subroutines. So they started with the SBR, which identifies it as a what? Subroutine. It's an input instruction, so they use one of their bit registers out here for what? Yeah, as an output. It's got to have an output, right? You understand that? And it's going to be true all the time. Then they're going to do, by the way, I think we have this one that we'll load in and look at. I think we have it on Logic. What you have to understand, if you come up here and you input these two outputs, you make them true, and then you go away from the subroutine, what's going to happen? They stay true. They stay true. Until, it's going to stay true until you come back to the subroutine, because it's not scanning the inputs in the subroutine anymore, right? It only scans the inputs in the subroutine when the subroutine is called. So if you turn one off, on, and then you go out of it, it's going to stay on until you do what? Until you come back to it. You don't. You just have to make sure if you want it off before you leave the subroutine, you do what? You turn it off. But you can't access bits in a subroutine without calling the subroutine. I don't know. Well, this one's going to come on instantly, so that this is a big problem here, is that they made these guys here unconditional. So as soon as I call the subroutine, then what's going to happen? It's going to come on, and then when I go away from the subroutine, it's going to stay on, it's going to stay on, it's going to stay on.
Even you can cut it off though before you leave out.
It's still going to be on, huh?
You can cut it off though before you leave out.
Yeah, that's what you would have to do, but they didn't want. They didn't do it in the book. Yeah. So you would have to change the program. This program wouldn't work. Well, it would. It would work one time, but after I called all three subroutines, then what would happen? So what's this figure number? I think I've changed it. Well, that's a non-rotating contact, yeah. So if the PLC turns, if the PLC loses power and then you turn it back on, it'll start the program back on the original scan. So all your outputs are turned off. RS Logics don't do that, but I think this is the one. Oh, wrong thing. So what figure is this? See which one this is. Okay. So what they did here is it automatically loaded them in. But what you're going to find out is that if you load in RS Logics, it's only going to load in the main program. And then if you want to see them, the subroutines will still run because they're part of the program. But if you want a tab down there to actually monitor them or something like that, then you're going to have to double click on it and add it to your what? To the list. So here's the subroutine here, and this is the subroutine here, and this is the subroutine here. So no, this is still the same. So let's go back to ladder 2, and we'll run this so we can see it. Okay, so we're running. Okay. So what are they using? They're using JSR. So let's look and see what the subroutines are going to do. So subroutine 1, which will be ladder 3. This is just going to turn on outputs 0 and 2, right? And then subroutine 4 should turn on outputs 2 and 3. And subroutine 5 should turn on outputs 4 and 5. And I think that was all the subroutines. And we'll go to run. Notice those two outputs come on instantly. Why?
And
Yeah, so we're using the accumulator of counter 5 for A, and then we're using a constant. We're using immediate addressing for source B. So it's saying, okay, is accumulator A, yeah, accumulator A less than 1. B. So it became true automatically. So we'll come up here and we're using switch 0, 1, 0. So let's turn this into a push button. Well, it would stay energized now, but even though I come, because it's still less than, right? Yeah, so here, this subroutine went true, but these guys here are still on. Because what? The program will turn off. And we're not scanning those inputs anymore, right? So as soon as we came out of that subroutine, just because it's out of the subroutine, if anything that's on, when you come out of the subroutine, it's going to do what? It's going to stay on. And then it says, we'll keep going. So I'm going to hit it once. Now notice, this guy here went false, but the lights that it controlled did what? Stayed on. Right? See that?
So does that involve like a latch or an unlatch to turn it off, or what exactly are you going to do to turn it off the program?
We would have to change the way the program runs, right? You understand? Yes or no? So what we would have to do is we would have to come in and you can't reset them, but you can clear them. Huh? Yeah, but we would have to add another option. So we'd have to do what we want to do with them before we return, right? So we could come in here and we could put another rung in here, right? And then we could come in here and we could put one. What do y'all want to press? Let's press
Put a time in there, turn it off after so long.
no, because that ladder is not being scanned anymore. It's only being scanned when you do what? When you're in the subroutine. So we would have to take care of that before we did what? Before we leave, right? Before we leave. We could put all kind of stuff in there I wanted to, but once it scans down through there and hits that return, right? You understand? So what we could do is we could probably come in and we could do this, right? You understand? And then I can put input, I don't know what time for break goes. 1/15. Okay. Everybody understand that? And then right here, I don't know if we would have time to do it or not. Let's do it this way. Now, if we wanted to clear a bunch of outputs, and we could put this in every rung if we wanted to clear them every time, what we could do is we could come up here and we got several options. So we can move 0 into what output are we using? Output colon. So what it's going to do now, it's going to call the subroutine, but it's going to stay in the subroutine until I decide when it comes out. Right? You understand that? So now, instead of it just going out there and doing something, I decide when it comes out. Now, if we just kept constantly jumping to the subroutine, right, then what we could do is we could go into that, or so I need to show you that. So let's download this. Okay, so those two lights come on instantly, right? Now, which subroutine did I
I
put
think
this in?
they're in 201.
I mean, two. Where did I put it in? Right here. Yeah, we're not gonna be able to see this. Oh, got it in right. Yeah, I know what's going on. Go take a break. I'll show you what I have to do. Oh, I know what I needed. No, this is the first one, right? This is 3. 3 is, no, the first one being called, yeah. So I would have to get to 3.
You have to reset, number.
It would be better to put it in this guy right here. So these guys are gonna stay on, but that's okay. I see what it's just okay. So we need to go up and make, I'm listening.
When you take one page, look through some of the classes that I've already taken, see what possible, whatever, to ISU. I know I have to contact one of those people, like a couple of the things, but just kind of give you an idea of what
We can try. Of course, I do lunch too. You know that, right? And I have to do it. No, I have to do a lunch. I've been diagnosed. I'm a type 2 diabetic. So you gotta
eat an interval.
right. But I do a protein break, and I think I take a snack. I don't need a lot. Okay, so what?
I was talking about it, just telling it, it's very simple, especially if it's a online class. Now you got it true.
Yeah, it's always true though.
Now you found out.
So this guy here resets everything.
Yeah. You gotta count up to 10 to get it to swap over to number 1 and then press 15. You got it on.
So I need to put this on ladder 4. And make this conditional. What we have here is we have conditional subroutines. Now, if you have unconditional subroutines, it looks like they're part of the main program. You understand that? So you can update the inputs instantly, just like they were part of the main program. If you got conditional subroutines, then they're only the outputs are only updated when you're what? That subroutine. So what we're going to do is we're going to come up here and make this true again. So right now I'm inside this subroutine right here, right? And what I've done is I've turned on the green lights. Now this is so this is always true. So now I can go inside there and I can do what? I can turn them off and on. So you say, well, I don't see it, but if we went over to the subroutine, you don't have to look at it. Here's my switch right here, and I can just I'm just clearing out. So y'all can see what I'm doing. I'm just moving 0 into my output port. And as soon as I move 0 into that output port, it does what? Clears it, right? And then if I go back to my main one, so if I leave it on though, and then I come out of the subroutine, then I go, now I'm going to make it false. So the other one goes true. And now these are going to stay on because they were on when I came out of the subroutine, so they're going to stay on, right? Understand? But now I should be able to control, I don't know why they're not. That was neat, but my wife, but now I'm doing something else. So now,
All the subroutines use the same output.
no, they're not using the same output. So the first subroutine, the first subroutine, what's my reset one? So the first subroutine is using outputs, are using outputs 2 and 3. The first one that's being called. Okay. So the first one that's being called is it's looking for less than 10. So it's going to call subroutine U4. So that's going to be this 4 down here is what this is. Makes sense? So this subroutine is running constantly now because this is always true. So what that means is I can come up here. Logic Pro's having a oops, wrong one. Yeah, it's updated.
You say you're moving 0, and this when you're inside the subroutine, you're moving 0 to the output port. I mean, what is that? I mean, you put 0 when it's looking for.
So to turn an output port on, you put a 1 in there. To turn an output port off, you put a 0 in a register. So this is not quite like what it looks like. And so here's my output register. Okay. So that's all that is it's a 16-bit storage location. We can turn that thing on and off with an input, or we can access them any way we want to, which is so dang neat. So I could come up with a method that I wanted to come up with. So I could come over here and change this move instruction over here in this other subroutine. I could say I could turn every other light on if I wanted to. So you can update a whole 16-bit output red port at one time. And you can, and that's where when we get into like shifts and sequencers and stuff like that, which gives us the ability. So right now, if I wanted to update multiple output ports, I would have to come out here and I'd have to put an output coil for every one of them. Right? Understand what I'm saying? But I don't have to do that because that output port responds to a memory location. You understand what I'm saying? So what that means is if I store all zeros into that output port, then all the output port goes to 0. Okay, understand?
Kind of like register that output.
Well, the output port is a data file, Now, we need to understand the difference between data files and registers, and the book gets that very confusing. A data file is something that I can manipulate. Registers are done inside the processor. So like the stack pointer, the program counter, and stuff like that, we have very little control over because that's inside the processor, and that's controlled by the operating system, the machine language operating system that Alan Bradley wrote. Okay. Then we get into these data files. This is nothing but RAM memory. What's RAM memory? What's RAM memory? Yeah, but I take it out further. I say it's random access read write memory, which means I can do what? I can read from it or I can write to it. So when the PLC is scanning, all it's doing is looking at that output 0, and if it sees a 1, it turns that output on. If it sees a 0, it puts that output in. Now by normal scan, we're updating that input, we're updating that output file with outputs, right? With O instructions. But we have access to that. So I could come up here and basically I could do anything I wanted to. I'll show y'all that in a minute. So I could turn on every other output. I could turn on this output. I could turn on that output without going to each individual output, right? You understand that? So, yeah, we just put whatever we want to in there. Well, we can read an entire input port if we want to. So instead of me putting this little thing right there, I can read the entire input port. And I can bring it into a register, and then I could turn around and take that input and send that to the output. Okay, I'll show you that in a minute. This Logic Pro is not doing it right. It did it a while ago. Yeah, this takes the place. We clear memory out all the time. Normally, if I do a reset, what we try to do is when we do a reset, then we can send everything back to its initial position. And that's usually what we can do here is, notice here, instead of using the move, I'm using the what? Clear. So this is going to clear word 0. That's what it's going to clear word 2. So no matter what's out there in that word, if I come up here and actuate that switch, then even though that rung is trying to turn them on, I'm putting a 0 out in that port, and what did it do? It did what? Turn them off. So it's pretty neat. And when we get into sequencers and stuff like that, where we're trying to deal with multiple outputs. So if I wanted to turn this motor on, turn that motor on, turn this one, turn that one, turn this one, turn that one, you could think about the logic. I could set that up in a table, the sequence I wanted that thing to go, the sequence, and I just send it to those ports, and the ports would respond without having 500 outputs. You understand what I'm saying? Yeah. Yeah, all these conditions, we can go through that. We can move around. It's really, really neat. And that's what's so neat with a computer. We can't do that garbage we can do sequencers, but you'll see a sequencer on a PLC. It's nothing but a bunch of cam gear. It's got cams all over it. And then it's got a motor that turns it. And then those cams, then limit switches hits those cams and makes the thing run into a certain sequence. That's the way we would have to do it on motor control, but here we just set up any type of sequence we want, which is pretty neat. We'll show y'all the bit shield. So all I'm doing here, and this is not quite responding right, is so now this subroutine is being called all the time, and now I have the ability to do what I want to with it, right? You understand? But if I turn these things off and I come out of that subroutine, they're going to say what? Off. Until we do what? Until we call the subroutine again. Now, unconditional subroutines, they'll update instantly. They look like they're part of the ladder. They look like they're part of it. So a lot of programs, like the one that runs the robot, those are not unconditional subroutines. Those are just written to split that program up into what? Into individual modules. But we can make them conditional. You'll find that too. But you got to remember, and it makes sense that if the subroutine is not running, then all your outputs are going to stay the way they were, right? Y'all understand that?
I understand your question. So you
you cleared that whole word on output two. You cleared that whole word.
That's why the others went off. Thank you. That's why everything went off.
Oh, so you clear this whole word. and then-
We could do it inside since we're dealing with an output port, we could clear them over here. We could clear those outputs over here.
Alright, so I'm saying if you clear them in one subroutine and then go back to another subroutine, it's like that whole word is now disabled. once you
Yeah,
go
what
back
I'm doing is I'm not doing it the way I should be doing it. The way I'm doing it is I'm clearing the output port. So I was trying to figure out why when I did this, it cleared everybody. Okay, so even those guys,
What I was getting to, like, in the different subroutine, with the outputs being the same output word, so when you reset that word, would it reset multiple subroutines?
yeah,
You know what I'm saying?
yeah, that's what I'm doing though.
Um,
So no matter what subroutine I'm in, I'm clearing that word.
right,
When I clear that word, it clears all the outputs.
all outputs, even if they're separate.
Yeah, so if I only wanted to clear the ones inside that subroutine, then I would clear a bit, right? You know what I'm saying? So yeah, when I hit this switch 14, it's gonna clear everybody. So what I'm saying is if I come over here, right now I'm in this guy right here. So I'm gonna come over here and go to the next one. So now he's up on this one. But I'm not clearing that subroutine. I'm clearing output 0. So notice what happens when I clear it. All of these. But as soon as I do that, so when I hit 14, all of them turn off. But the only one I'm controlling now is 1 and 0 because that other subroutine is not running to do what? To make them true. But yeah, but all we're trying to illustrate is that if you need an output in a state when you come out of that subroutine, then you gotta put it in that state when you come out, right? Especially a conditional subroutine. If it's unconditional, it's gonna run all the time anyway, right? If it's conditional, if you come out of the subroutine, whatever state your outputs were in when you came out of them, they're gonna stay in that state until that subroutine does what? Runs again. And this one don't run them again. Once it's through with them, it's through with them. Make sense? Are you okay? Gotta move on, guys. Nested subroutines, and this is what we're talking about. So nested subroutines is when a subroutine calls a subroutine. And this is pretty neat. So if I've got two modules two program files that need to do the same thing, well, instead of me repeating those rungs inside every module, so let's say I got every module that needs to check an input. Well, or check 5 inputs. Well, instead of me putting those 5 inputs inside every module, inside every subroutine, then I can put it out here in another subroutine on its own, and then let each subroutine call that section up, right? And how does it know its way back? Yeah, the return. So, and we can go level. So this is an example. This is not in your textbook. This came right out of the Allen Valley rule. So this is saying jump to this subroutine. It goes over there, saves everything for this one, goes to this subroutine. Then it says what? Jump subroutine. It goes to this subroutine. Well, it says the return on the stack, but it's on top of a stack, right? You understand? Then it says what? Jump sub comes over here, right? Okay. Runs this subroutine. He hits this return. Where's it going to go back to? It's not going to go all the way back to that. It's going to go back to the program file that called it. And this is going to come back to this one at the next run. When it hits this one, it's going to come out of this one and go to the right run. When it hits this one, it's going to go back to the right run. And then it starts the whole scan again. These are called nested subroutines. And we do this a lot. Because you understand, I have a module, so instead of me keying in all this information, and it's exactly the same thing in every one of my subroutines, then I can have a subroutine called another subroutine. And it knows its way back. It automatically knows the path back, right? You understand that? And we call these what subroutines? Nested. And it's just like that plate. You know, you pull the plates off, and you come up here and you start writing information on the plates, and you're putting it in that thing that automatically goes down. And that's what it's doing. It's writing this information and it's putting it on there. And then it's writing the information where the next one's at and putting it on there and putting it on there. And then what does it do? It pulls the plates off one at a time. Right off this thing called the magic stack. And we use that a lot. That's what allows us to do subroutines and allows us to do interrupts too. Interrupts. These are subroutines, but these are initiated by what? Hardware. Y'all know hardware, right? So JSRs are initiated by software. You decide where those are at. Interrupts, the interrupts are initiated by hardware, right? And so we have what we call if the interrupts that scan the main program. This is not quite true. We can put interrupts in an interrupt can occur anywhere, any subroutine it can occur. Okay, y'all understand that? So an interrupt occurs. What does it do? Well, it saves where it's at. How does it say where it's at? On the stack. Then it goes out there and runs the interrupt service routine. And the interrupt service routine has to end with a what instruction? Return. And then that'll bring it back to the whatever program file was running at the time when the interrupt occurred. We have several. We have a literal hardware interrupt. Now, for the 504, you have to buy an input module that supports interrupts. So if this guy here don't support interrupts, which it don't, then we don't have hardware interrupts. Usually, like the 1100, it assigns certain input ports that you have to use if you want to use hardware interrupts. So you sacrifice one of your input ports to indicate a what? An interrupt. One of the interrupts that these all supports, it's called and this is optional too, even though the book doesn't say that. What you need to do is if it's an interrupt subroutine, the first instruction you need to put up there is INT, right? You understand? Everybody understand that? And on your regular subroutines, you need to put an SBR, even though they're optional, because that way when you look at the program file, you know automatically it's a what? Interrupt or a standard software subroutine. We have what we call a selectable time interrupt. This guy here is cool. We have some task that's got to be performed on a regular basis. One thing would be if I'm trying to precisely control the speed of a motor. Well, what we want to do is we'd like to go out there at a short time and constantly do what? Check it to see if it needs it. We have we have different ways we can precisely control the speed or how things change. Like control temperature. If I had to have an exact temperature somewhere, we could put a temperature sensor out here, and if I set it at 70, it'll turn the heat on. And then, okay, it comes up here, and it hits 70, but what's going to happen? It's actually going to go above 70 something, right? You understand? And then, okay, so it cuts it off. And then what it'll do, go below 70. So what happens, using this, we call it proportional control, is your system's constantly doing what? Pulsing, yeah. So it's constantly doing this. We call it oscillation. So your motors, they'd actually go, and sometimes you can't hear it, which is not really good on a motor. So what they came up with is it takes a little algebra, but if you understand it, they call it a PID control. It's proportional for just basic proportional, and it's integrals, which is a trig, and differential, which is calculus. So basically, what integrals does is look at what happened in the past. And what the differentiator tries to do is anticipate what's going to happen in the future. And when you combine these three things, you'll end up with a control that comes up here, and right before it gets there, it'll start doing what? It'll level it off, and it'll run just perfect. We call them PID controllers. But if you're going to use a PID control, you better take care of that guy at a what? At a fixed interval. You better take care of it. Because you can't let the motors seek too much, right? You understand? So here, you're running this ramp up here, you're increasing the speed of the motor, and you're not running your PID math. And then it's going to do what? Now it's going to overshoot, not because it's just that you wasn't running the logic that was telling it when to start slowing down, when to start ramping, right? You understand that? So if you're running a PID control, then by George, you better have in your control logic, you better go out there and do what? Constantly do what? Monitor it. So you could just put the rung all the time, and right? You understand that. But what would be better is if we just set it up as a what? A timed interrupt though. And we say, I want to go out there and check it every second. Well, what you would do is you would set up this guy, and I don't think RS Logic supports it. So this is it. So what you do is you go out, and this is in your project tree. I don't think RS Logic supports it. But what you have is you have these files right here. No, that's not there. Over here, you have what we call function files. You'll see that? And then when we open up the function files, this is your timed interrupt. So STI is not an instruction. STI is because if it was an instruction, it wouldn't be a hardware interrupt, right? You understand that? So the book is kind of misleading. But when I come up here, this is what I would do. So right here, I would specify which file or which subroutine do I want to run. So this would be like anything above 3, right? Unless you're if you're using MicroLogic 1000, it's ladder 5. You have no option because that's a fixed PLC. So that means if you look at your project tree and you're using the 1000s, you've already got everything you can have in that thing. So you can't create a new subroutine file or program file. You got what you got over there. Well, this guy right here, if this was the 1000 that I was doing this on, 5 would be in there already. So you can't select that program file. So I would put a 5 in. So if I wanted to use ladder 3, I would put a what? I would put a what? 3. Now all these are just information, but then I would come down here and I would put a 1 in this file right here. So I would come here and I would double click on this and and I would put whatever program file I wanted to put in there. And then this is, so you have to set this up, right? You understand? And then I would come down here and I'd tell it to enable user interrupt. And then I would come down here and say, well, I want to enable my timed interrupts. And then I would come down here and I say I wanted to do it every second. Well, then I would put 1000 in there because this is in milliseconds. And then as soon as I exit out of this, then automatically it would start doing what? It would start scanning ladder 3 every second. And whatever's in that program, whatever's in that interrupt subroutine, it would do that, and then it would come back. When it hit the return, it would come back to the main program. So now what we've done is we're letting the hardware, we're letting this clock inside that thing. This is still hardware because there's a clock inside the PLC that's keeping up with this for us, right? You understand that? And so this is still hardware, but what you have to do is you have to do what? You have to come up and set it. Now you can change the time and you can enable it with an instruction called STS, which is, where's our interrupts at? Would that be in? Let's see if it's in program control. If it's not, it's in miscellaneous. There it is. This is STS. This is an instruction. And what this does is you can set the time there. So you don't have to set it in the STI file. You can set it there. Okay? Does that make sense? Maybe not. But what you have to understand, and like we said, we're not going to do a lab on this. It's just that something you got to keep in mind that you understand the importance of a hardware interrupt, right? So instead of me putting a subroutine inside my program, I can set it up so something outside can say, hey, I need to do this. So I need to do that. And I gave you an example of the way the scan works. So how does a scan work? So it goes to everybody in the class, one at a time. Like, Christine, are you true or false? Bernard, are you true or false? And that's the way the scan goes. Goes through all your inputs, right? You understand? Okay. But what happens when I've got to honor an input? I've got to honor an input, right? You understand? Then we need to set that up as an interrupt, right? You understand that? And this selective time interrupt gives you the ability for the hardware in the processor to automatically at a set time come back and run a routine. Are we okay? This guy I think you can use the first 5 inputs. I'd have to go look as interrupt input. This guy though, when you buy your input module, you have to buy it to support what? Interrupt. And you would set that up in the IO screen that you have over. Are we okay? So any questions on that?
Yeah, so general, INT goes on the main program.
No, the INT, oops. I don't think this guy right here don't have that, so I can't do it here. I don't think. Let's look at the instructions and see what's available in Logic Pro. I don't think any of the interrupts are available in Logic Pro. Oh, this is the only one we have. So let's see what instructions they control. I think it was in the miscellaneous section. Yeah, see, so Logic Pro don't support any interrupts. And what I'm going to do is I'll make a new one. I'm going to tell it not to say anything here if it asks me that. Yeah, but it's a hardware initiated subroutine. We don't call it a subroutine because we don't want to get interrupt routines confused with software subroutines. So what we call it is we call it an interrupt service routine. That's the technical name that I've always learned how to call it.
Instead of allowing logic to come through,
It's called by hardware. So they're always conditional, but it's conditional on some type of hardware. So I need to show y'all the clock too, which is really, really neat. You can actually see the clock, and you can use it too, by the way. I'll show that. So here's our, if I wanted to make an interrupt service routine, then I would come up here, and the only thing different is that when we set the thing up, we'll just make another ladder called INT, and then we'll open it up. Then what we would do is we would come up here, and this is optional, but you need to do it because it identifies the difference between an interrupt service routine and an actual subroutine, right? So the first instruction we would put on here is, let me do this. The first instruction that we would put on here, by the way, y'all see what I did? Here's the palette of instructions right here. And instead of you trying to go back and forth, back and forth, back and forth, this is every instruction that the PLC recognizes. So there's your basic bit instructions. And so what we can do is we can pull them out of here instead of having to go through all those palettes. So what I would do first is I would come up here, and they're in alphabetical order, so they're not in groups. So you'd have to know the mnemonic. So it's here. So I would come up here and put this, and that lets me know that it's what? Interrupt service routine. And then of course I would come over here, And then I could use, one of my bit files, which would be this guy. And then I could come up here and assign this, oops, not Rich. So B10, this guy recognizes the B10, right? And I might use 200, something I'd never ever use. Oops. That'd have been a big one, wouldn't it? And then I'm not going to give it a label. But you can also give it a symbol or whatever you want to, right? Understand? And then what I would still end it with is I would still end it with a what? Yeah, I'd still end it with a return.
This is like, the main program that you talk, right?
Well, on the main program, what I have two options. I can come up here and so I could come up here and put this instruction in there. And what it's going to do, it's going to fill in a lot of information for it. So STI is not an instruction. STI is basically a configuration file that we go in and set. We also have another thing available where I can come out here and put STS. Now, STS is an instruction. And it's an output instruction. And we just come up here and we set a time. So I can change the time between the interrupts, right? You understand? I can do that through software, but I can't set up the STI through Easy. We could, but it would be a lot harder to do. Okay. So what I would do though, to actually set up the selected time interrupt, I would come up here and double click on files. Then I go to STI, and then what I have to do, I have to select a file number. But this can be anything between 0 and 255. Right? You understand that? Of course, before I put what? I put 3 because that's the one I wrote it at. And then what I would do, then I'm going to have to enable user interrupts. And we have access to this through an instruction, by the way. It's called, I can't remember what it is. And then we would come back here and enable the time interrupt. And then right here, we don't have to do anything to that because as soon as I run the program, it's going to stick 1000 in there for me. That makes sense? Because of this instruction right here. That's what you're doing. With this instruction right here, you're going to set this time. I could put something in there. I could come up here and I could put 5000 in there, but as soon as the program runs, it's going to come in and that's going to wipe it out for me. And so what we've done is we've set up this, so of course we won't be able to clear this up. I don't think it'll, let's see if it'll. So it said, no, it says, so it says there's really no instructions in there. So I'd have to build the program up. So STS is an optional instruction, and this allows you to change the time. You can enable the interrupt from here, you can disable the interrupt from here, but what you can do is you can change that. Now we do have some instructions. I don't know if the book covers those, where we can enable it with an instruction and disable it with an instruction. That's not what I want, Rich. So every section in the programming manual has a section on interrupts. And it explains the interrupts, kind of like the So this instruction right here, so if I put a UID instruction, this would be what? Disable the user interrupts. If I put a UIE instruction, this would be what? Enable it, right? And if I did this one, this would flush all the interrupts that's in the stack.
So for reset.
Yeah, it's kind of reset for interrupts. So what you're doing is no, you disable it. It's just like me, I'm up here lecturing and I see somebody raise their hand, right? You understand that? Well, if I didn't have the ability to disable that, then it's gone. Right? You understand? But if I can say, okay, hold on, that's what we have the ability to do. So if I'm running a section of my program that cannot be interrupted, like updating my PID control, then I could turn it off until I update it, and then I could turn it back on when I come out of there, right? You understand? So we have the ability to enable and disable these interrupts, just like me when I'm up here lecturing and you have a question, you raise your hand. If I didn't disable that in my brain a little bit, I'd stop in mid-word. Well, that's not true. I'd get through with the current instruction, but I would stop after that word and I'd say, and I'd say, okay, what's your problem? Right? But what do I usually do? I go ahead and disable my interrupts for a little while. I go ahead and finish my thought. I get to a point where I can do what? Then I say, okay, what's your question? Well, that's what these instructions would be right here. These instructions would what? They would hold them off if I've got a critical thing that cannot be interrupted. If I interrupt it, it's going to cause problems, right? You understand that? Like controlling this PID control. If I interrupt that situation when I'm trying to figure out this math, and it's pretty complicated math, to make sure I control the speed of that motor or temperature. I've got an oven melting steel. Well, by George, it's got to be a precise temperature to do what I need to do. And I don't want to interrupt that while I'm like checking the temperature of an oven, or I'm checking the temperature of a metal, or if I'm checking this or checking that, then I have the ability to disable the interrupt for a little while. Now if you disable it, you got to remember to what? To enable it. Because if you disable it and you don't do it, it's
When I asked you about the flush, you said it's disabled. So then, like, what is the main difference?
well, the flush would flush out the stack. So all these interrupts, we can have interrupts within interrupts, right? You understand? So if I don't disable it, then what it'll do is it'll finish the rung, it'll go out there, but then I might have another interrupt. Well, it'll go to that one. Well, how does it keep up with where everything's at? It keeps up with the stack. But I come over here and I got this reset button on the front of my thing, and I want to reset the whole system. Well, what I want to do is I want to flush all those interrupts out. So on my reset routine, I would hit that reset button and it would flush the interrupts out. Now, if they still needed my attention, they could interrupt again, right? You understand? But usually when we hit a reset button on the front of a system, we want to go back to the what? To the beginning. And that's what's so neat about these output ports. You could put these output ports in any state you wanted it to be in, right? Y'all understand that? Any state, it's not time. Any state you wanted it to be in. But see, I've got you interrupted, right? So let me show you. We can do this with RS Logic real quick. And it's so neat, you know, so I could come in here and I can update these ports any way I want to. So this is Logic Pro. So we'll start a new program real fast. No, this is not it. This is RS Logic. Don't get confused, Rich. So what I'm going to do is I'm going to go over here to my move instructions. And I'm going to say X, and then I'm going to put that in output 1/. I'm gonna put that in output one, 0. I'm gonna put it in the whole word, right? You understand? And then I can come up here and I could make another input. And then I'll come over here and then I can move, and then I can move that into output 1.0. Oops, sorry. We're still in program. It's actually 2, right? 2.0. That's what I'm doing. What I'm doing is I'm updating 16 bits at one time, whatever pattern I wanted to put in there. Now I know that AAAA turn on every odd bit, turn on every odd bit, and 555 hex would turn on every even bit. So what I'm doing here is I'm just jumping between the two patterns, right? So that's AAAA. But what we're talking about is these output ports are nothing but memory. Well, not true. The outputs are strictly outputs, but the PLC, to determine whether the output is true or the output is false, it reads a memory location. And it's RAM, which means what? It's read-write memory. So I can put anything I want to. So literally, I can put anything in any output port I want to, and that output will respond without having a push button, right? You understand? I can anything I want to out there. And that's what the beauty of a PLC is. So I could literally come up with a sequence right here to come in, right? And I could store it every time, and we'll look at later on a sequencer, where we could move it into different locations, and then I could just read, and then I could have like a timer that would just shift between those locations, right? Somehow. And then it would update the outputs without me saying, is this true? Is that true? Or anything like that. I can come up with any sequence I want to. So isn't that neat? Let's see that. And this would happen on the real PLC too. So when I press this button, I'm moving this hex number in there. And when I press this button, and this is one reason you need to know binary. Because if you don't know binary, then you'd say, well, what decimal number do I need to do to turn on every other port? You'd have to write down that 16-bit number and go up and turn that into decimal. So if we want to enter hex, we use a what at the end. H. If we want to enter octal, we put a what? O. We don't want to use B, even though you can, but it gets very cumbersome to enter 16 bits of B, right? Everybody okay? Okay, I'll take it back. Go to lab after lunch. So I know how far we got, so I know how to set up the review. So I'll get up the review as soon as I can. It's hard for me to do it today, though, guys. Tuesday. Huh? I don't know. We take the begins on how long. It don't take me long to do lunch though, because all I do is drink an energy drink.
I was going to grab a salad.